In section 9.4, we're going to look at another type of differential equation, a special type. This is a first order linear differential equation, and it's the derivative equal to the function y plus some constant b. So this particular form is not separable, because if I minus k times y of t to both sides, I'm not going to have a product of the derivative times the function. It's going to be a subtraction problem instead. However, if your differential equation does look like this, the general solution, y, is going to be some constant times e to the kt minus b divided by k. For example, number 1, if I wanted to find the general solution to this differential equation, notice that k is going to be equal to 3. It's the number on the y, and b is equal to 7. So the general solution, y of t, is simply the constant c e to the 3t minus 7 over 3. Really nice form, very easy to work with. In example 2, well, it's not quite what I need, but if I go ahead and get the derivative by itself and add 2y to both sides, I can see that k is equal to 2. Oops, and this should be a minus 8. Sorry, k is equal to 2, and b is equal to negative 8. Okay? Our solution, y of t, will be equal to c e to the 2t minus negative 8 over 2, which would turn into a plus 4. And then we have our initial condition that y of 0 is equal to 0. So if we have 0 is equal to our constant, e to the 0 is just 1, plus 4, that tells me that my constant is equal to negative 4. Our specific solution would be y of t equal to negative 4 e to the 2t plus 4. So a little bit of review. Going back to the different types of solutions we can have. If we have an equilibrium solution, so this would be our equilibrium solution here. If we have an equilibrium solution and all the solutions approach our equilibrium solution, we say that our solution is stable. And let's say that we have an equilibrium solution where all the solutions move away from our equilibrium solution. Then in that case, we say that this equilibrium solution is unstable. So now looking at example 3 says to find the equilibrium solution. Okay, so that's where the derivative is 0. Make a sketch of the direction field and determine whether the equilibrium solution is stable or unstable. So if I set the derivative equal to 0 and I solve for y, so add 1, multiply by negative 2, I have y is equal to negative 2. So this is going to be our equilibrium solution. And we need to determine whether it's stable or unstable. So what we're going to do is we're going to graph this. So I'm going to make a sketch. And now my equilibrium solution is at -2. So I want to get my graph big enough so that I have -2 in here. Oops, this should be a 3. All right, so the equilibrium solution, yeah, I'll stay with, no, I want to change my colors. I'm going to go with green. So this is my equilibrium solution. Now, if I look at y is equal to 1 as a test point, and maybe I'll go to 1, and I put that in my derivative, if y is equal to, -1, my derivative is going to still be negative. And in fact, if I put in any y value greater than -2, my derivative is negative. So that means my little tangent lines will have a negative slope, and it will be approaching my equilibrium from above. And I know my direction fields are pretty sad, but you get the idea, right? Okay, so this is my, I'm getting really lazy. This is my direction field from above. Now if I put in, say, -3 into my y value in my derivative, then my derivative is going to be positive. So lower than -2 derivative is positive. And I could see that the equilibrium solution is stable because all my solution curves will approach my equilibrium solution. Now in example 4, we're going to look at an application of this type of first order linear differential equation. We have a drug that's administered intravenously. So the drug is going in at a rate of 5 milligrams per hour. So the amount of drug in the bloodstream can be modeled by this initial value problem. Okay, so T is in hours. And the rate at which the drug is entering the bloodstream is -0.03 y plus 5. So we want to find the solution to that initial value problem. And it looks like it's of the form ky plus b. I can see that k is -0.03 and b is equal to 5. My solution, general solution, is then y of t equal to c e to the -0.03 t, and then it's going to be plus 5 over 0.03, right? Because the minus turns to plus. Now I think I could write this in a better form of y of t equal to c e to the -0.03 t. I don't like the decimal in a fraction, so I'm just going to change this to 500 over 3. The initial condition is that y of 0 is 0. So if y of 0 is equal to 0, then that means that 0 is equal to if t is 0, this is just c, plus 500 over 3. So C is equal to negative 500 over 3. And the solution to this initial value problem is y of t equal to, now C is negative, oops, got a bunch of keep marks on there, negative 500 over 3 e to the negative 0.03t plus 500 over 3. So it actually is nicer if we go ahead and factor out the 500 over 3. What's left over in parentheses, I'm going to switch around and write it as 1 minus e to the negative 0.03t. This is the solution to my initial value problem. Now when we look at part B, B says to sketch the graph of y, okay, from part A. And on your calculator, you should use the window of x values from negative 1 to 500, okay, and y values from negative 1 to 200 to get a nice picture. My sketch will be a little sad because again I'm hand drawing this. When t is equal to 0, notice that we have 1 minus 1. So y is equal to 0. And I'll be here. In my calculator, the graph kind of does this. And then it starts to level out. It turns out that what it's approaching is 500 over 3. So in part C, we're supposed to find the steady state or equilibrium level of the drug. And that would be the quantity that our graph approaches, right? Because that's a stable equilibrium solution, says that your curves approach that equilibrium solution. So there's different ways that we can find the equilibrium solution. We can simply just look at the graph. The graph is approaching 500 over 3. So by the graph, I can see that my equilibrium solution is 500 over 3 milligrams. And when we're talking about drugs, we typically call that equilibrium solution the steady state. That's as the drug remains steady in your body. Okay? Or the amount going in is the same as the amount going out. Another way we can find the equilibrium solution is by taking the limit. If we take the limit as time goes on or approaches infinity of my function y, which is 500 over 3, 1 minus, now because of the negative exponent, this is actually 1 over e to the 0.03t. So think about this as the limit, as t goes to infinity, this fraction here is going to be approaching 0. So this limit is equal to 500 over 3. And that would be another way that you can find the steady state or equilibrium. Part D says, when is the drug at 60% of the steady state value? So let me move over a little bit. Let's call this D. We have our solution y. When it's at 60% of the steady state, that means that y is 0.6 for 60% of the steady state. Okay. This is going to be equal to 500 over 3 minus 1 minus e to the negative 0.03t, right? So here, this is when our y value is equal to 60% of the steady state value. So solving this equation, I could see that the 500 over 3, I can cancel that out. And we have 0.6 is equal to 1 minus e to the negative 0.03t. Or in other words, I have minus 1 and then multiply both sides by negative 1. I have 0.4 is equal to e to the negative 0.03t. Natural logging both sides, I have the natural log of 0.4 is equal to negative 0.03t. Okay. And then dividing both sides by the negative 0.03, we have the natural log of 0.4 over negative 0.03 is equal to t. So that's the exact value. Now if I put that in my calculator, I get 31.4 something. So I get approximately 31 hours if I were to round it to a whole number. This is actually a very short section because we were looking at a specific type of differential equation that had a specific type of solution. In the next section, 9.5, we're going to look at applying separable and this type of first order linear differential equation to some application problems. So that's it for 9.4.